We present the method for ID to reflectance, monocular identity-conditioned facial reflectance reconstruction. The Mona Lisa gazes at everyone with her calm smile. Given a photo of the Mona Lisa, our ID to reflectance can reconstruct her facial reflectance maps, including diffuse albedo, specular albedo, roughness, and normal maps for a realistic relighting effect. To produce pore-level reflectance reconstruction, the industrial pipeline typically employs professional equipment, light stage to capture high-quality multi-view gradient images. High-quality reflectance maps can be obtained through multi-view stereo, material solving, texture mapping, and manual post-processing by the artist. However, this approach is too complicated, extremely costly, and difficult to generalize quickly. In order to solve the problem of reflectance reconstruction using a data-driven approach, recent Albedo first proposes a 3D statistical albedo model with separate diffuse and specular albedo priors. AvatarMe synthesizes diffuse and specular colors for high-quality textures by training an image-to-image translation network using limited light stage data. Based on the data from AvatarMe, FitMe proposes a BRDF generative network and a two-stage fitting method to predict facial reflectance for unconstrained images. Relightify utilizes a powerful diffusion model to infer diffuse, specular, and normal. While the AvatarMe, FitMe, and Relightify series perform well in facial reflectance reconstruction, neither the synthesized reflectance data nor the light stage captured reflectance data has been released. The assets available for purchase are also limited. Generating your own assets through post-processing can be quite costly. Given these challenges, we are exploring how to reconstruct facial reflectance from a single image using only limited raw data. We first captured a limited amount of raw data using light stage. Here is an example of our raw data. As you can see, these facial reflectance data have the same facial structure, only differing in appearance. Our key insight is this shared structure will enable obtaining expressive facial prior from inexpensive RGB data, thus reducing the dependency on reflectance data. That is, we can model face structure by a large amount of RGB data and appearance by limited reflection data, separately. Our ID to reflectance pipeline has 3 steps. We first train a high-quality facial reflectance model through a multi-domain codebook learning scheme based on the pre-trained multi-domain codebooks and a pre-trained face recognition model. We train face swapping in the RGB domain and automatically transfer the swapping capacity to the reflectance domain. In the end, we design a simple yet efficient inference framework to achieve monocular high-quality facial reflectance map reconstruction. In the first stage, we simply train the quantized autoencoder with a shared codebook using both high-quality facial RBG and reflectance data. In the second stage, we train domain-specific codebooks and fusion module to further improve facial reflectance reconstruction. Here are the TSNE distribution figure and the visualization of codebook fusion weights. These figures show that reflectance data uses multiple basis codebooks for discrete representations, which indicates the alignment behavior between the reflectance domain and RGB domain. We explore training identity swapping in the RGB domain and automatically transferring the identity swapping capacity to the facial reflectance domain. Specifically, we propose an identity condition swapper module and integrate it with the above-learned quantized autoencoder. After swapping, we stitch the 3-view reflectance images to get the final reflectance map. We first evaluate our method in the task of monocular facial reflectance prediction. Following recent state-of-the-art methods, we perform visual comparisons on the well-known digital Emily and in the wild data, respectively. To evaluate the impact of template selection, we randomly select a Chinese male adult template and provide stepwise qualitative results. Even though the reflectance template is fixed, our method still attains a high level of identity preservation. The only difference is the skin tone color in diffuse albedo. We also visualize some relighting results of our method. Given the ethnicity-diverse template library, our method is capable of reconstructing a wide range of races, producing relighting results at superior quality. Here are more relighting results via hard inputs. We also perform ablation studies. The input and reconstruction results from the RGB and reflectance domains demonstrate that the joint codebook has limited capability in recovering cross-domain data, leading to visible artifacts and an oversmoothed face structure. By contrast, our multi-domain codebooks achieve finer facial structure and better reconstruction quality. Besides, we compare our swapping module with state-of-the-art methods. Our approach achieves consistent and high-quality swapping results on both RGB and reflectance domains. Thanks for your watching.